Hello everyone, in this lecture I will go over sequences in math and how they're defined and what the properties of the sequences are, and then I will talk about proof by induction and how we can prove some theorems about sequences using induction. We begin this lecture by defining a sequence. A sequence is a special type of function in which the domain is a consecutive set of integers. So a sequence is a function, but the domain has to be a consecutive set of integers. The expression g subscript k is called the term of a sequence, and the variable k is called the index of that term. When a sequence has finite domain, we call it a finite sequence. When a sequence has an infinite domain, we call it an infinite sequence. If you have a finite sequence, there's an initial index like m and a final index like n, where m and n are both integers, and n is greater than or equal to m because n is the final index, m is the initial index, so n should be greater than or equal to m. Then a sub m would be the initial term, and a sub n would be the final term, where a is used to represent the terms of that sequence. A sequence can be specified by an explicit formula showing how the value of term a sub k depends on k. So basically the term will be dependent on the index value when you have an explicit formula for that sequence. In the next slides, I'm going to show you some examples. So here is a sequence. As I told you, a sequence is nothing but a specific type of function with a specific domain. So the sequence that we're talking about here is called SK. So we use capital S to represent the terms of that sequence. And the subscript is K, so when we say S sub K, it means that the term of the sequence with index K. So this is how the sequence is defined. This is a finite sequence. S sub 1 is equal to 2, S sub 2 is equal to 5, S sub 3 is equal to -1, S sub 4 is equal to 7, S sub 5 is equal to 8. So basically the domain, which is the set of all indices, is 1, 2, 3, 4, and 5, and the value of the terms are 2, 5, -1, 7, and 8. So if you consider a sequence as a specific type of a function, then the domain would be the set of integers 1, 2, 3, 4, and 5, which is a consecutive set of integers, and the range is the elements 2, 5, -1, 7, and 8. Basically, this sequence S maps 1 to 2 and 2 to 5. It maps 3 to -1, 4 to 7, and 5 to 8. So this is how a sequence can be defined like a function. But this is a more common way of representing a sequence, in which you represent every term by adding an index to the symbol of that sequence, which is S. So S1 is the term that 1 is mapped to. S2 is the term that 2 is mapped to by S. S3 is the term that 3 is mapped to by S. So in this finite sequence, we call 1 as the initial index, because 1 is the minimum value in the set of all indices or in the set of domain. So the initial term is also called is equal to S1, which is 2. So the initial index is 1. The initial term is equal to S sub 1, which is 2. 5 is the final index because it's the greatest index in this example, and then the final term is 8, which is the equal to S sub 5. Now let's look at the infinite sequence. This is an example of an infinite sequence, A sub k, where the index of ak, which is represented by k, can be equal to 1, 2, 3, all the way to plus infinity. Basically, the index of ak is the set of all positive integers, and this is how you represent the sequence. So in brackets, in curly braces, we write down ak, and this represents the infinite sequence ak. Then for this infinite sequence, we use an explicit formula to represent it and to define it. So A sub k is defined to be equal to 1 over k. Therefore, if you set k equal to 1, then ak would be 1 over 1, which is 1. If you set k equal to 2, then we have a2 equals 1 over 2. A10 is equal to 1 over 10. So all you need to do is, when you are calculating A10, you need to plug in the value of k in the explicit formula that you have. So if you write down the first few elements of the sequence, then the sequence looks like this. The first element is 1, then 1 over 2, 1 over 3, 1 over 4, and this list continues forever. A1, which is equal to 1, is called the initial term of the sequence, but since this sequence is infinite, it doesn't have any final term. So far, we have mathematically defined a sequence, and we have seen a few examples of both finite and infinite sequences. Here, I'm going to define some properties of a sequence. First of all, we start with increasing sequence. A sequence is called increasing if for every 2 consecutive indices k and k plus 1 in the domain, ak is less than ak plus 1. So the next term would be greater than the previous term. So for any 2 adjacent terms, the term with a higher index should be greater than the other one. A sequence is called non-decreasing if for every 2 consecutive indices k and k plus 1, ak is less than or equal to ak plus 1. So the definition of non-decreasing and increasing is almost the same. The difference is here for increasing we have less than relation between ak and ak plus 1. For non-decreasing we have less than or equal. Okay, same for decreasing and non-increasing. A sequence is decreasing if for every 2 consecutive indices k and k plus 1, ak is greater than ak plus 1. So when you have 2 consecutive index, when you have 2 consecutive terms, the one with a lower index is greater. And the definition of non-increasing sequence would be the same as decreasing sequence, except that inequality that instead of greater, we have greater than or equal. So these are the 4 properties of a sequence. We can find a sequence that has none of these properties, but a sequence can have at most 2 of these properties. Then we define two specific types of sequences. One is called geometric sequence, one is called arithmetic sequence. A geometric sequence is a sequence of real numbers where each term after the initial term is found by taking the previous term and multiplying it by a fixed number called the common ratio. For example, an equals 2 to the power n is the explicit formula of a geometric sequence where n is any positive integer. So the sequence looks like this. If you replace n by 1, then you get 2 to the power 1, which is 2. Replace n by 2, then it would be 2 to the power 2, which is 4. Then you replace n by 3, you get 2 to the power 3, which is 8. Then we have 16, 32, and this pattern continues forever. So why do we call this sequence a geometric sequence? Because after the initial term, the consecutive terms can be found by, or can be calculated by, multiplying the previous term by 2. So 2 here is the common ratio for this geometric sequence. For example, 4 is equal to 2 times 2. 8 is equal to 4 times 2. 16 is equal to 8 times 2. 32 is equal to the previous term, which is 16 times 2. So that's why we call these sequences a geometric sequence, because after the initial term, every term can be found by taking the previous term and multiplying it by a fixed number, in this case 2. Then we define another specific type of sequences, which we call them arithmetic sequence. An arithmetic sequence is a sequence of real numbers where each term after the initial term is found by taking the previous term and this time adding it by a fixed number called the common difference. So in the arithmetic sequence, every term would be the previous term plus some constant value, which we call the common difference. In the geometric sequence, every term would be equal to the previous term multiplied by a number, a constant number, which we call the common ratio. So in arithmetic sequence, we have addition operation between the two consecutive terms. In geometric sequence, we have multiplication operation to find the next term of the sequence. So this is an example of a arithmetic sequence. A sub n is equal to 3 times n minus 1, where n can be any non-negative integer. So basically the sequence looks like this. If you replace n by 0, then an would be negative 1. So a sub 0 is negative 1. If you replace n by 1, then a sub 1 would be equal to 3 times 1 minus 1, which is 2. If you replace n by 2, then you get 3 times 2 minus 1, which is 5. Replace n by 3, 3 times 3 minus 1 is 8. Replace n by 4, 3 times 4 minus 1 is 11. And this list continues forever. So as you see, a term like 5 is equal to the previous term, which is 2, plus the common difference, which is in this case equals to 3. And 8 is equal to 5 plus 3, which is the common difference. 11 is equal to 8 plus 3, which is the common difference. So the common difference is the 3 that is coefficient of n in this explicit formula for the sequence. So far we have seen that a sequence can be represented by an explicit formula that is a function of the index of a term. So in the explicit formula of a sequence like an, we would have a function of the value n, which is the index of term an. But there's another way of representing a sequence, which is to use a recurrence relation. What is a recurrence relation? A rule that defines a term like an as a function of previous terms in the sequence is called a recurrence relation. So in order to illustrate how recurrence relation looks like, let's consider the case in which we want to define an arithmetic sequence using the recurrence relation between its terms. So between any two consecutive terms of an arithmetic sequence, there is a relation like this, which is an equals d plus an minus 1. In other words, the nth element of the sequence an is equal to the term with index n minus 1, the previous term, plus a constant value, which is d. D is called the common difference. But this is not enough to define that arithmetic sequence. We need to define its initial value. So we say the first term, the initial term a0 is equal to a, and then obviously after defining both the initial value and recurrence relation, you can calculate any term that you want. For example, if you want to find out a sub 1, you need to plug in you need to replace n by 1 here, and a by 1 would be equal to d plus a sub 0, and a sub 0 is a, so a1 would be d plus a. If you want to find out the value of a2, then you have to replace n by 2, then a2 would be d plus a1. a1 was calculated as a plus d, so a2 becomes 2d plus a. This way you can calculate any term with any index value. All you need to do is, if the index is 10, you need to use this recurrence relation 10 times, so that you can find a1 first, then a2, then a3, then a4, then a5, all the way to a10. So using the recurrence relation, you can calculate the terms step by step, one by one. First you need to find a1, then you find a2, then a3, then a4, then a5, then a6, and this way you can calculate all other terms in the sequence, but in a step-by-step way. As the second example of recurrence relation, you can see how we define a geometric sequence using a recurrence relation. The initial value is a. It's a constant number. We can replace a by any number that you want. So this is a0 is equal to a. That's the first equation that we need for defining a geometric sequence using a recurrence relation. Then we say a sub n, which is the nth element in the nth term in the sequence, or the term with index n, is equal to r times an minus 1. an minus 1 is the previous term, or the term before an. So an is equal to its previous term times r, where r is a constant value and it's called common ratio. So this is how the recurrence relation of a geometric sequence look like. Let's assume that r is 2 and a is 1. So a sub 0 would be 1, and then a sub 2 would be 2 times 1, which is 2. A sub 2 is 2 times 2, which is 4, and then this way you can calculate all the integers, or the terms with any index that belongs to the set of all positive integers. So this is how the recurrence relation of a geometric sequence looks like. Another example of recurrence relation is when you're defining a sequence like Fibonacci sequence. The Fibonacci sequence is a sequence that is defined in the following way. The first two elements, the first two terms with index 0 and 1 are defined in the following way. an is equal to n. So this is the explicit formula for the first two, or for the first two terms, or the initial term and the second initial term. So a0 is 0, a1 is 1. And then after defining the initial values of the Fibonacci sequence, we need to find the recurrence relation between the elements of the Fibonacci sequence. This is how the recurrence relation looks like. Every term is equal to the term with index n-1, which is the previous term, plus an-2, which is the two previous terms. So if you add two terms, consecutive terms, you will get the next term. So this is how the sequence looks like. The first two terms are equal to 0 and 1, because an should be equal to n for n equals 1 and 2. Then the third term with index 2 would be equal to the summation of the two previous terms, 0 plus 1, which is 1. So this is 1. And then in order to calculate the fourth element, the fourth term, you need to add the second and third term. 1 plus 1 is equal to 2. In order to calculate this term, you need to add 2 and 1. 2 plus 1 is 3. In order to calculate 5, you need to add 3 and 2. 3 plus 2 is 5. Same for 8, same for 13. Why this term is 13? Because 8 plus 5 is equal to 13. This is a famous sequence, Fibonacci sequence, that can be easily defined using a recurrence relation. But if you want to know, you can represent Fibonacci sequence with an explicit formula too, but that explicit formula would be very is much more complicated than what you see here. You can Google it and find out how the explicit formula of Fibonacci sequence looks like, but this is much easier. This is a much easier representation for a Fibonacci sequence. An is equal to an minus 1 plus an minus 2, and the two initial values are 0 and 1. A sub 0 is 0, a sub 1 is 1. This slide introduces a notation for summation of numerical sequences. If you want to add a number of terms together, then you need to use the following notation. We have a summation in the following way. You write the general formula, or the explicit formula of a sequence like AI, and the index is represented by I here. I is a variable, and then AI would be in front of a symbol like this, which is the capital sigma, which is an alphabetical, which is a Greek alphabetical letter, and in this notation we represent the lower limit and upper limit of I in the following way. We say I is equal to S all the way to T. T is the upper limit of the summation, S is the lower limit of the summation, and variable I can vary from S, which is the lower limit, to T, which is the upper limit. And when I varies from S to T, we generate different terms of this sequence an, and after generating all of those terms, you add them all together to calculate this summation. So in this summation, variable I is called the index of the summation. The variable S is the lower limit, and variable T is the upper limit of the summation. As an example, if you want to calculate this summation, j from -1 to 2, j squared plus 1, what you need to do is to first replace j by -1, then you replace j by 0, j by 1, and j by 2, and this way you can calculate the 4 terms of the sequence j squared plus 1 that is participating in this summation. So if you set j equal to -1, this term of the sequence would be equal to -1 squared plus 1, which is equal to 2. If you set j equal to 0, then the term would be 0 squared plus 1, which is 1. If you set j equal to 1, then the term would be 1 squared plus 1, which is equal to 2. And if you set j equal to 2, then this term would be 2 squared plus 1, which is equal to 5. So the summation would be 2 plus 1 plus 2 plus 5, which would be equal to 10. So this is the final result of the calculation. So in the second part of this lecture, I'm going to talk about mathematical induction, which is a method of proof for predicate that is defined over a consecutive set of integers. After showing you the structure of this proof, I'm gonna talk about why this method is correct and the correctness of mathematical induction, and then finally we're gonna see an example of how to prove a theorem using mathematical induction. So let's begin by assuming that Sn is a statement or a predicate parameterized by a positive integer like n, and assuming that you have this predicate where n can be any positive integer, then you can prove that Sn is true for every positive integer if and only if first you need to show that if you replace n by 1, then S of 1 would be true. This is called the base case of the mathematical induction, or the base case of proof by induction. So you need to prove that S is true, the statement is true when you replace n by 1, which is the smallest value in the domain of n. Secondly, you need to show that for every k in the set of all positive integers, if sk is true, if s of k is true, then s of k plus 1 has to be true. In other words, for every positive integer k, s of k should imply s of k plus 1. This is called the inductive step. In this statement, sk implies sk plus 1, which is, this is the inductive step of the induction, mathematical induction. The supposition that S of k is true is called the inductive hypothesis. So S of k is called the inductive hypothesis. Sometimes it is represented by IH, which is a short form of inductive hypothesis. So in the inductive step, we need to show an implication. S of k implies S of k plus 1. S of k, which is the hypothesis of this implication, is called the inductive hypothesis. Now, it is important to know that the principle of mathematical induction states that if the base case, when n is equal to 1 or n is equal to the minimum value of the domain, is true and the inductive step is also true, then the theorem holds for all positive integers. What does it mean? It means that proving the inductive step and base case or basis step are enough to prove that the statement parameterized by a positive integer like n is true for all positive integers. In order to understand why induction works, consider the following statements. First of all, let's assume that we are going to prove a predicate like p of n, where n is any positive integer. As mathematical induction states, we have to first prove the basis case, which is p of 1. Let's assume that we prove p of 1 is true, and for every k greater than or equal to 1, p of k implies p of k plus 1. This is what the inductive step states in the mathematical induction method. So, assuming that k is equal to 1, if you replace k by 1 in this inductive step, then obviously p of 1 implies p of 2, because you replace k by 1 here, so it would be p of 1 implies p of 1 plus 1, which is 2. So if you replace k by 1 in the inductive step, p of 1 implies p of 2. Since p of 1 is true based on basis step, therefore p of 2 has to be true. Now, if you replace k by 2 in the inductive step, p of 2 implies p of 3. And since p of 2 is true based on the previous conclusion that we had, then p of 3 has to be true. And again, if you replace k by 3, p of 3 implies p of 4, which means that since p of 3 is true, p of 4 has to be true. And since p of 4 is true, p of 5 has to be true. Since p of 5 is true, p of 6 has to be true. So the final conclusion is an infinite chain of conjunctions p of 1 and p of 2 and p of 3 and p of 4, and this list goes forever, has to be true. This infinite conjunction of p of 1, p of 2, p of 3, p of 4, etc. can be summarized into this universally quantified statement: for every n greater than or equal to 1, p of n has to be true. If you remember, I told you before in the first chapter that, or in the second chapter, that if you have a group conjunction, you can replace it with a universally quantified statement like this. So that conclusion is logically equivalent to this universally quantified statement. For every n, p of n has to be true, and this is what mathematical induction wants to prove. So finally, I'm going to show you an example of proof by induction. You can see more examples in Zai book in chapter 6. At the end of the section regarding induction, you can find a number of examples, and I have made the solution to those exercises visible to you, so you can look and learn from those solutions. In this slide, I'm going to show you an interesting theorem which says for every positive integer n, the summation of all integers from 1 to n is equal to n times n plus 1 divided by 2. I'm going to use proof by induction to prove it. So I have to show two statements. One is called the base case, the other one is called the inductive step. In the base case, you have to set n equal to 1, and this way the left hand side of the equation would be the summation of all integers from 1 to 1. So when we replace n by 1, the upper limit would be 1, which is the same as the lower limit, and therefore in this summation we only have one term. and that term is equal to 1, so the left hand side will be 1. The right hand side of the equation can be calculated by replacing n by 1. So if you replace n by 1, you get 1 times 1 plus 1 divided by 2, which is equal to 1. So both left and right hand side of the equation are equal to 1. Now let's look at the inductive step and see how we can prove the inductive step in this example. Suppose that for some positive integer k, the summation of all integers from 1 to k is equal to k times k plus 1 divided by 2. This is called the inductive hypothesis. This is obtained by replacing n by k in the original equation. Assuming that this is true for k, the equation is true for k, we should show that the equation is also true for k plus 1. So if you replace n by k plus 1, you get this conclusion. Equation of summation of 1 to k plus 1j equals k plus 1 times k plus 2 divided by 2. In order to prove this equation, I'm going to start from the left hand side of the equation and try to reach to the right hand side. In the left hand side, we have the summation of integers from 1 to k plus 1, which can be separated and written in the form of the summation of all integers from 1 to k plus the last term, which is k plus 1. So we are separating out the last term from the rest of the summation. Why? Because if we do that, then we can replace this summation from 1 to k by what inductive hypothesis claims, which is k times k plus 1 divided by 2. And then after that, since both of these terms have a k plus 1 in common, you can factor out k plus 1 and the left hand side, and if you factor out k plus 1 from these two terms, the remaining parts would be k divided by 2 plus 1. You can get a common denominator for these two terms that are adding together, and then you get k plus 2 divided by 2 in the second parenthesis of this expression. And then finally you can make it in the same way that it appears in the right hand side of this conclusion. So in order to prove this equation, we started from the left hand side. We used some algebraic operations and the inductive hypothesis to prove that it is equal to the right hand side of this equation. So we are done proving the inductive step, therefore we are done proving that theorem.